think we're going, aren't we? Well, let's start. Okay, this is Friday paper 22, and I am going to start by doing problem number 5. And then it says, select all relations that are functions. And so a function is when you have a relationship between x and y such that the x's never repeat. In other words, let's take a look at this. If I have this equation for a, y equals 3x plus 5. Every time I put something in for x, something different in for x, I'm going to get something out for y. So I have an input and I have an output. So like if I put a 2 in for x, well, let's start at 0. Let's start easy. If I put a 0 in for x, 3 times 0 is 0 plus 5 is 5. Okay. And then if I put a 1, 3 times 1 is 3 plus 5 is 8, right? And this is actually going to be a linear relationship or a linear function. So this is a function, okay? For every input, I have an output, okay? So notice here in this relationship, when I put in a 2, I got out a 4. And here I put in a 2 and I got out a 9. So function machines don't work that way. Remember those function machines we talked about that you had in elementary school, where you had when something goes in, something's going to come out. And in this case, my input of 2 gave me a 4, but it also gave me a 9. So this is not a function. For this graph, it's a linear function, right? Just like letter A, it makes a line. And if I could zoom in, I don't know if I could zoom in that far. 1, 2, 3, 4. It looks like the B might be 4. And the M, oh, that's going to be hard. Let's make this up. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe, who knows? Something like a slope of negative 5/9. And then I could write y equals negative 5/9 plus 4. That's slope-intercept form. So if I can do that, let's put an x. Then I have a linear function. So this is a function. This y equals negative 1/2 x. For those in Algebra 1, this is a direct variation. We just talked about this. It's written in the form y equals kx, and negative 1/2 is the constant of variation. It is the constant of proportionality. In other words, the y-intercept, y equals mx plus b, the y-intercept is 0, right? And this looks very much like a linear function because it is. And so we're going to put D here. So here I'm putting in a negative 1 and I get out a 5. I have putting in a negative 2 and I get out a 3. Put in a negative 3 and I get out of 6. This has no repeating x's, right? They don't repeat. So we're going to call that a function. Okay, let's go ahead here. Evaluate and put your answer in scientific notation. Okay, so we're going to first, it's a multiplication problem. So we're going to multiply these numbers first. And I'm going to make use of what property tells me that I can multiply these in any order. The flipping property, commutative property. So I'm going to take and do that. 18, 12, 13, and there we go. And then it's going to be that 13.8, 13 and 8/10 times 10 to the 4 plus 3. Remember, when our bases are the same and we're multiplying those monomials, we add them. But question, is this in scientific notation? Remember, this first number right here has to be between 1 and 10. And right now it's bigger than 10. So we're going to have to move that decimal, and we're going to be moving it to the left. We're going to make it less. So by doing so, I need to bump this power up to still remain equal. So we get 1 38/100 times 10 to the 8th power. Okay. Now we're in scientific notation. Good. Let's look at this one. So it says, remember to distribute first. And it just says simplify. Why doesn't it say solve? Because it's not an equation. There's no equal sign. I can't solve it, but I can simplify it. That doesn't mean I'm going to get one answer, like x equals 3, which is what I would get when I'm solving an equation often. So we're going to just go ahead and we're going to treat this as if it were one side of an equation. This is an expression. Okay. And when we simplify expressions, we follow some steps. We're going to distribute if we need to, and we do need to distribute. And I'm just going to rewrite the rest here. And then I'm going to combine like terms. So combine like terms. And remember, when you're doing that, make sure you grab the sign in front of the term. Let's do something that looks a little different here. I have a positive 8 and a positive 10. Those are like terms. Those are my constants. And then I have my terms here that have my variables. The 4 is called the coefficient of x, right? So let's go ahead and take 4x minus 6x. So I get negative 2x. And then I have a positive 8 and a positive 10. That makes a positive 18. Can I combine any further? No, those aren't like terms. So my answer is this. So this whole expression goes on the line. Notice we took the first expression and we simplified it, but that's as simple as we can make it. Okay, so that's my answer. This whole thing that I just circled, negative 2x plus 18, is the answer for number 8. Let's go on here to number 10. Now I'm interested to know if you remember these things. A lot of times it comes up in elementary school, especially if you have a fifth grade teacher who likes math. If they don't love math, they might kind of just skip over this part. And that's supposed to be a straight line, by the way. It could have come up in 7th grade, maybe. I drew a right angle, okay? And then this is a straight angle or a straight line, right? Let's pretend we have this here just to kind of give you an idea. It looks like it's opened up all the way, this one. And if it's a clock, right? This is the 12 and this is the 3. And if this is the same clock, this is the 3 and this is the 9. Can you imagine that on a clock? Those are like hands on a clock. So when I have a right angle, this is 90 degrees, right? This is a 90-degree angle. And when I have a straight line, right, this angle measures 180 degrees. And a lot of times we draw this like as an indication of the angle that we're measuring. And so we can also put the degree sign. And so we could label this one A and label this one B. And we could say the measure of angle A is 90 degrees. So the measure here of angle, it's not less than, that's an angle, of angle B is 180 degrees. Okay, that's just to kind of give you kind of a reminder of some of those terms that we use. So it says here, what is the complement Oh, nice hairdo today. Oh, your teeth look so straight. Oh, your angle is so nice and right. No, that's not a compliment, although it is. The compliment is when you have, think of it like this. Here's your 90-degree angle, right? And it says I have a 38-degree angle. That's probably going to be somewhere like this. So let's pretend we have this angle right here. And we're going to call this one A. Okay. So the measure of angle A is 38 degrees. And so when we have a complement to that angle, we have to figure out what is the measure of this angle right here that will add up to 90 degrees. So I think about it like this. See this word complement? I have it over here. Let me get another color. I can write, see how I just did that? I just kind of drew a little line there and it makes a 90. Do you see how that is? The word complement, you can actually make the number 90 out of it. So two angles that are complementary angles are those angles that add up to 90. So how could I solve that? Well, I'm going to take 90, right? And I'm going to subtract 38. And I'm going to get 52 degrees. So the complement of the angle that is 38 degrees would be 52 degrees. Now, supplementary angles add up to 180 degrees. So a 90 and a 90 add up to be 180. So we can look at the question that we're given, and in this case, we're told we have this 180 degree angle, right? That would be half of a clock, half of a circle. And we know that we have this part, that same part, right? That is a 38 degree angle. And the measure of angle A is 38 degrees. So I need to know the measure of this angle right here. And I need to know what that would be. So the supplement to angle A has to add up to 180. So I'm going to take 180 and I'm going to subtract 38. And I'm going to get 142. That's 142 degrees. Now here's a little trick. Cool thing. If you look at the word supplement, do you see? It's so tiny. If I draw this line right there, does that kind of look like an 8? And I can put a 1 and a 0. See how the S in supplement kind of looks like an 8? 180. Oops, not 188, 180. That's one trick I use to remember the difference between complement and supplement. Complementary and supplementary. What a lovely angle you have. The width and length of a rectangle. Okay, this is a cool thing. This is when I remember when I did this. I think I did it in 7th grade. And I remember the teacher teaching me about this guy named Pithagoras. And Pithagoras was kind of a crazy dude. I encourage you to look him up. He actually ended up having kind of a cult following, kind of the religion of math. And so he's pretty cool, this ancient guy. And he came up with this concept, and it is now called the Pythagorean theorem. And a theorem is something that you can hear the word theory in it. A theorem is more like, hey, this is how something works. So we're going to use this theorem. So here I have a rectangle, and the width and the length are 6 feet. and 8 feet. Okay. And the question is, what is the length of the diagonal? So I'm going to call this missing one C. Now, if we were to put this on a coordinate plane, right, we could kind of envision this as like, do you know how we have a line and we want to find the slope of the line, right? The rise, and the run. Let's go here. The slope here, rise and run. And so you can kind of imagine this has a rise of 6 and a run of 8. So the slope of this line would be 6 over 8 or 3 over 4. Okay. So you can kind of picture things like that. He pictured stuff like that when he was doing this, and he also thought about it in terms of other shapes. And we'll get into that a little bit more when we get to this in our lessons. But the cool thing here is he found something that works every time. And that is, if I could call this A and I could call this B. The two lines that come together to make the 90-degree angle, we call those the legs. So this is a leg and this is a leg. So there's 2 legs in this right triangle. We're not even going to really think about this one right now. We're just kind of marking him out. And we're just focused on this right triangle. And what we're trying to find is this letter C. See this? I called it C. And that part of a triangle, which is the longest side, which is opposite the right, here's the right angle, it's opposite the right angle. It is called the, see where I could write it so that it makes sense, Hypotenuse. Ooh, I feel like I did not spell that right. Let's see. Spell hypotenuse. Hypotenuse. Yes, the longest side of a right triangle opposite the right angle. Boy, that's just what I said. Let's see what pictures they have here. Very good. Look at this one. Hypotenuse. Here's a 90-degree angle. That's some trigonometry. Trigonometry is a subject, a lot of it is based on, here's the one I wanted to show you. Yeah, this one. Let's see if I can zoom in on that. Algorithm, Pythagorean theorem diagram. Okay, cool. I think I can zoom in on that. Can it let me? Okay, so here's the cool thing. What he discovered was for any right triangle, if you took the length of side A and the length of side B and created a square, in other words, A right here times A would be A squared. Isn't that what the, will it let me, I don't know if it'll give me a laser. Ooh, I got a laser pointer. A times A is A squared, and B times B is B squared. And what he figured out was this A squared plus B squared is going to be equal to C squared. So the length of the hypotenuse squared. It's super cool. And let me just see if there's any other pictures that can help you see that. No, this is talking about vectors. Vectors are pretty cool things. Looks pretty good. So let's go ahead and apply that here. I sure hope you could see all of that. Your tab is being recorded. That means when I just went off of the tab, you didn't see it. Rats. All right. Sorry about that. So we're going to come back here and we're going to pretend what I just saw. Apologize. Let's see if I can make this think I have my laser pointer on. Yellow. Here's the B. And here's the A. Imagine a square that's 8 by 8. And this one is 6 by 6. What's 6 squared? 36. And what's 8 squared? 64. And what Pythagoras discovered is when you add those together, you can find the length of the hypotenuse. I'm going to erase this right here. And I'm going to draw a giant, just going to kind of go off the edge. Imagine it's C by C, which is C squared. C squared. So A squared plus B squared equals C squared. And we figured out A was 8, so 8 squared is 64, and B was 6, and those are interchangeable. I could have switched those around. Is 6 times 6, which is 36, is equal to C squared. So let's add those together. 6 plus 4 is 10, 6, 7, 8, 9, 10. 100 is equal to C squared. So the area of this square, if I can imagine one, would be 100. I want to just find what C is, right? So if I know something squared is 100, to undo squaring, I take the square root. The square root of C squared is C, and the square root of 100 is 10. 10 times 10 is 100. So what is the length of the diagonal? 10 feet. Beautiful. Okay, last one. Name all equations that have a solution of x equals -5. I have a feeling I do not need to work this all out for you. What you're going to do to solve is you're going to just substitute x for -5. So one strategy is to just solve these, and the other strategy is to plug in the -5. So I'm going to start by just solving them. So I'm going to add 10, and I get 2x is equal to -20 plus 10 is -10. Divide both sides by 2. X is equal to -5. Is that a solution? Yes. So far, so good. Let's add 12. Add 12. Okay, so 4x equals 10, 2, 3, 4. Divide by 4. X equals 10. Nope, doesn't have x equals -5. Now, I'm going to go ahead and do this one. Half of something is -10. To undo that multiplication, half of something, I'm going to multiply by 2. Multiply by 2 over 1. So that becomes 1 and 1. So x equals -20. Nope, doesn't work, does it? Let's try this one. Divide by 2. X equals 5. Nope. And finally, divide by -4. X equals -5. Perfect. So this one here, they are correct. So A and E. All right. Well, I hope that was helpful to you. I apologize that I went off there and you couldn't see it. Hopefully you got what you needed. I hope you have a great week. Love you guys.